Here I have an Arduino fading an LED on and off, and if you have used an Arduino before, you have probably done this using the Arduino's analogWrite command, because this is a very common introductory tutorial to control the brightness of an LED. However, here is a little secret about the analogWrite command. It is not generating a truly analog or continuously variable output voltage. It is actually generating what's called a pulse width modulation or PWM signal. The Arduino's I/O pins can only be high or low. They are digital, so they can be either 5 volts or 0 volts, but nothing in between. You can't set one to 2.5 volts. At least that is true for the pins on the Arduino UNO R3, and most of the pins on the newer UNO R4, which does have one true analog output pin, but that's a topic for a separate video. So what this PWM signal is doing is rapidly turning the pin on and off, but the frequency is high enough that the human eye cannot perceive the flicker. So rather than seeing the LED blink or flash or turn on and off very quickly, I just perceive it at a lower brightness when it's not on 100% of the time. You can also use this exact same concept to control the speed of a motor. Rather than using an analog voltage to adjust the speed, you use a PWM signal, for example, to have the motor on half the time and off half the time, but as long as the frequency of that signal is fast enough, we're not actually going to see the motor start, stop, start, stop, start, stop. It's just going to spin at a lower speed. Now, again, most introductory Arduino tutorials will have you just do this using the analogWrite function. In this video, we are going to learn how to generate this PWM signal manually using timers. And to do that, we are going to need to switch over to the computer and explain what timers are and how they work on the ATmega 328P, or the microcontroller that the Arduino UNO R3 is based on. Okay, to understand timers, we first need to just talk about the concept of a basic stopwatch. So say you have a stopwatch that measures time in hours, minutes, and seconds, and you hit start on that stopwatch. Eventually it's going to count up to some maximum value that it can hold, like 9 hours, 59 minutes, and 59 seconds. And then it is going to overflow or wrap around back to 0 because it can't hold any numbers bigger than that. There is no digit to go up to 10 hours here. So the timers on a microcontroller work much the same way, except they're not counting hours, minutes, and seconds separately. They're just counting in binary. So I have a separate video explaining how binary numbers work that I recommend you go watch first if you're not sure, because I'm not going to go over it here. But the ATmega 328P has 3 timers available. 2 of them are 8-bit, and 1 of them is 16-bit. We're going to focus on the 8-bit timer as an example here. So this is a timer that is storing 8 bits in what's called a register, or a specific location in the microcontroller's memory. So when that timer starts out counting at the decimal equivalent of 0, so this is the binary value here, decimal value over here is just 0, it's going to count up until all of the bits in that register are 1. So 1, 2, 3, 4, 5, 6, 7, 8, which is equivalent to a decimal value of 255 for an 8-bit timer. And then it can't go up any higher than that. It cannot count to 256 because it's out of bits. So it is going to overflow and wrap back around to 0. So again, same concept as a stopwatch that just kind of runs out of space, except instead of counting hours, minutes, and seconds separately, we're just counting 1, 2, 3, 4, and so on, up to 255. We can't go to 256, so we overflow back to 0. The next question is, okay, well, how fast is it counting? Is it counting up every second here, or what? And the answer there is that it depends on the microcontroller's clock speed. So a microcontroller has a clock signal at a certain frequency. For the ATmega 328P, that is 16 megahertz. So this is just a very precise square wave that it uses to kind of keep track of time, but it's not measuring seconds. It is a 16 megahertz clock. So if we calculate the period of this square wave as period equals 1 over the frequency, which is 1 over 16 times 10 to the 6th hertz, we are actually going to get a period of 62.5 nanoseconds. So that is the period of 1 clock tick. So the timer as it counts up, it is counting up once every clock tick. So that's important. It's not measuring seconds. Each one of these ticks is 62.5 nanoseconds. So kind of a weird unit of time, but that's what we're measuring here. You have to remember that in the future when you're converting between clock ticks. If you actually need to get time in seconds, you have to use that conversion factor of one clock tick is 62.5 nanoseconds. Now, just like a stopwatch, our timer has different modes or different operating things it can do. The first one is just called normal mode. This is just kind of like starting your stopwatch and letting it run up until it overflows, and we're gonna show what that means on a graph here. So on the y-axis of my graph, I have timer value, and then on the x-axis, I'm gonna have clock ticks or time in nanoseconds, where again I'd have to remember to multiply by that 62.5 to convert clock ticks to nanoseconds, but either one works for the x-axis here. So on each clock tick, my timer value is going to increment by 1. So it's going to start out at 0, tick up by 1, go up to 2, and so on. So if I zoom in close enough, I'm going to see kind of this staircase function, but if I zoom out, I'm not really going to see that. If I'm not zoomed in close enough, it's just going to look like it's counting up linearly. Again, if I zoom in close enough so I can see the individual clock ticks, then I'm going to see the staircase or step function. But if I zoom out, I'm just going to see the timer value counting up until it hits whatever that max value is, which again, for an 8-bit timer, is 255. So I kind of have this ceiling at 255 that my timer value can't go past, so it's going to count up until it hits that, and then it's going to overflow back to 0, and then it's just going to keep counting up again. Again, just think of this like your stopwatch that hits 9 hours, 59 minutes, and 59 seconds, wraps around to 0, and keeps going. So I just turn the timer on in normal mode. It is just going to keep going along, doing that until it overflows, come back down to 0, and then go back up again. Now, since I know that it's going to take 256 clock ticks to overflow, remember we start counting at 0, so there's 256 periods in there, not 255. If I want to calculate how long that takes in seconds to overflow, I can multiply that by my 62.5 nanoseconds, and I'll get 16,000 nanoseconds or 16 microseconds to overflow, which on a human time scale is pretty fast, but on a computing time scale is a pretty long time. So if I want to measure how long something takes, I can start when my timer is 0 and then say some event occurs here, some certain amount of time passes, and I can grab the value of my timer, which is stored in this register, and say, okay, that took this many clock ticks. I'm going to convert that to seconds and measure how long it took. Now, if more time passes and the timer has overflowed, for example, say I've gone here, 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 and now my event occurs here, then if I just measure from 0, my elapsed time isn't going to be correct. I would need to keep track of how many times the timer has overflowed since I started and make sure I am counting those times as well, and then my final time here. But that's kind of a topic for, I have a different video about, for example, measuring how long a button is held down. Here we're just explaining how timers work so we can get to using them to generate a PWM signal. Okay, so that is normal mode. We also have another one called clear timer on compare. On compare or CTC mode. And how this mode works, instead of always counting up to that max value of 255, we can choose the value at which we want the timer to be cleared or reset. So I can choose this value to be somewhere between 0 and 255, and now my timer is going to count up, and rather than going all the way to the top, it's going to reset there. So that allows me to control this period by moving this value up and down. I can change this period, and then, for example, if I want to fire an interrupt or make a certain event happen at this fixed period, something like blinking an LED without using delay commands, which is another popular project or way to introduce this, I can do that. And again, I have another video explaining that, so I'm not going to go over it here, but I wanted to mention the idea of this compare value or output compare, because that is what we are going to use to generate a PWM signal using a different mode. So remember that our goal with a PWM signal is to generate a square wave, and we want to be able to control the duty cycle or percentage of time that this square wave is high. And you might look at that and say, okay, I'm just going to do that with digital writes and delays. I'll use a digital write high to turn a pin on. I'll use a delay to wait a certain amount of time. I'll use a digital write low to turn the pin off, and then I'll use another delay to wait until I turn it on again, and just put that in a loop. And I'm just going to toggle the pin on and off and adjust the delays to adjust the duty cycle. And technically that would work, but the problem is your program is then kind of stuck in that loop, just waiting in these delays for the next toggle. And while you could technically jump out of that loop using interrupts, which are a topic for another video, that's going to then mess up your timing and get your frequency slightly off. So ideally what we would like to do is kind of generate this PWM signal automatically or in the background while letting our program go on to do other things. And that is what we are going to do using a timer PWM mode. So there are many different PWM modes in the ATmega 328P datasheet for the different timers, which we are going to switch over and look at next. I'm not going to go into the details or exact differences between all of them in this video, but we are going to talk about kind of the general mode of operation. So when you set the timer to PWM mode, rather than just counting up and resetting, it's going to count up and then back down. So it's going to go like this, kind of make a triangle wave instead of a sawtooth wave. And just like with, clear timer on compare mode, we are going to choose that output compare value. And that is a value that we store in another register that for an 8-bit timer is going to be between 0 and 255. But the PWM mode is going to do something different with this output compare value. It is not going to reset the timer when the timer reaches that value like we had in clear timer on compare mode. It is going to toggle one of the Arduino's pins high or low when the timer crosses that value. So this functionality is linked to the hardware pins. So to illustrate that functionality, we're going to draw a second graph where this is now our pin voltage. So this graph up here is representing PWM mode. This is still our timer value. And this is still either clock ticks or nanoseconds over here on the x-axis. And now we have our actual pin voltage. So this is going to go between 0 volts and 5 volts on the Arduino output pins. And what happens is it is going to toggle the value of that pin each time the timer value, well, it is either up counting, so this is, and this is down counting. It's going to toggle the pin value. So if the pin value starts out low, then when this cross happens, then the pin value is going to go high. It's going to wait until the next cross, go down, so on. So I'm not going to draw all of them, but you get the idea. Or if the pin value starts out high, and we'll talk about later how you can choose between these two options, then it's going to do the opposite. So here, pin value is going to start high at 5 volts. That's going to cross. It's going to go low to 0 volts, and so on. So same concept. You have the choice between these two options, and we're going to talk about that when we get to the registers in a minute. But I find the second option actually to be a little more intuitive, because remember that this output compare value can be between 0 and 255, and say I increase that. Okay, I'm going to increase it up here and make it higher. Well, if I, again, trace down where these are going to cross, in this case, making that higher is actually going to decrease the duty cycle. So it's kind of an inverse relationship, making this number bigger. Again, where this is a value between 0 and 255, and our duty cycle is going between 0 and 100%. Making the output compare value closer to 255 gets the duty cycle closer to 0. Whereas here I have the opposite and what I believe is more intuitive behavior. If this starts high and I increase that output compare value, now it is going to be low for less time. So for this option, making the output toggle low when the timer is up counting and high when the timer is down counting means that having your output compare value between 0 and 255 linearly corresponds to a duty cycle between 0 and 100%. So either option works. Again, I found this one, that's OC output compare duty cycle, more intuitive. And again, if you're familiar with the Arduino analogWrite command, that is how that command works. So analogWrite takes a pin number and then a value where value is between 0 and 255, and a higher value there is going to give you a higher duty cycle. So analogWrite is using this version, but if for whatever reason you find this one more intuitive or want that inverse relationship, you can use this version. They're both valid, and you can select them using the timer control registers, which are going to decide which mode the timer is and how this PWM functionality is working. And that is what we are going to look at next. So the first thing you will need to do is look at an Arduino pinout diagram, and you can either Google this and find the first-party one on the Arduino website, or there are a bunch of good third-party ones out there like this. And as you probably know, if you've, again, done this before, only certain pins on the Arduino are capable of PWM, and they are marked with the little squiggly symbol there. You see the PWM label here. So you want to find the pin you're using and then look at which output compare it is connected to. So the UNO R3 has 3 timers, each of which have 2 output compare registers, which is what gives you a total of 6 possible PWM pins. The timers are timers 0, 1, and 2. So I can see that pin 3 here, which is what I had my LED connected to back at the beginning of the video, is connected to timer 2 output compare B. So that is what the OC2B means here. Once you have found that, you are going to need to switch over to the ATmega 328P datasheet, which is this massive 400-page document that can be pretty overwhelming the first time you look at it, but I am going to walk you through using it specifically to set up PWM using timer 2 as an example in this video. If you selected a different pin, the process is going to be the same, but you're going to need to find different pages in the datasheet. So there's this giant table of contents over here on the left where you can see TC0, TC1, TC2. Those are timers 0, 1, and 2. You can also Control-F and search the document for TCCR2A. That's timer 2 control register A. For timer 1, it's going to be TC1 control register A, and so on. So in the version of the datasheet I am on page 203 for TCCR2A, timer 2 control register A. But if you have a different version of the datasheet or you're using a different timer, you are going to be on a different page. So an overview of what we're looking at here. There are 2 of these timer control registers we're going to care about in this video, TCCR2A, and if we scroll down a few pages, we will eventually get to TCCR2B. And these timers have a bunch of individual bits that are, these registers are going to have a bunch of individual bits that control the operation of the timer and these different modes we talked about earlier. So if we look at table 22.9, waveform generation mode bit description, and look at this column sort of in the middle here, we see a bunch of the modes we talked about earlier in this video. So we have normal mode, we have CTC, which is clear timer on compare mode, and we have a bunch of different PWM modes. And again, in this video, I am not necessarily going to go into detail about the differences between all the different PWM modes. We are just initially going to want to select mode 1, phase correct PWM, and get some information from this table for, okay, how do we set this timer to phase correct PWM mode, and what's the relevant information we need? So the first thing to note here is that the top value that the timer is going to count up to is 0xFF, and if you're wondering what in the world is that, that is a hexadecimal representation of the number 255, which written out in binary would take 8 bits, so this is just a more compact way to write that. I have a separate video about how hexadecimal numbers work that you can check out separately if you want to learn more about that. The next thing we want to look at here is what are the values of the WGM or waveform generation mode bits that will set the timer to mode 1. And we can see from this row on the table, that is going to be WGM22 is equal to 0, WGM21 is equal to 0, and WGM20 is equal to 1. So if we scroll back to look at the actual register description, we will see that each bit in the register has a name, and we can see where the waveform generation mode bits are in the register. And you might say, wait a minute, only 2 of them are here in TCC R2A. There was a third one somewhere, and that is because the third one is down here in TCC R2B. There we see our other waveform generation mode bit. Now, we're not done yet. We got a lot more bits to deal with here. So we have these force output compare, or FOC bits. Luckily, we don't need to worry about them. We're just going to leave them set to 0. Over here, we have the CS, or clock select bits, which if we scroll down to table 2210 clock select bit description, we say these are the bits that are going to let us select that prescaler that I mentioned earlier. So the prescaler slows the timer down by a fixed factor. So there are only certain options available, 1, 8, 32, 64, and so on. So for example, if I choose a prescaler of 8, that is going to make the timer only count up once every 8 clock ticks instead of every clock tick. And we'll talk more about how we could use that to adjust the frequency of the PWM signal later. So far, we've really been focused on changing the duty cycle. But note here that if those bits are all 0, then the timer is stopped and not doing anything. So in addition to setting it to the PWM mode that I want with the waveform generation mode bits, in order to actually start the timer, I need to set the prescaler to 1. Note that there's this weird missing digit in the datasheet here, but this should be a 0 in that cell. So I need to set my clock select bits to 0, 0, 1 in order to turn the timer on. Still not done. We are jumping all around the datasheet here, and don't worry, we're going to recap all of this in a minute since there's so much scrolling back and forth. We're going to go back up to timer to control register A and look at these COM bits. So COM to A1, COM to A0, and so on. And see that there are a bunch of different tables describing what these bits do, but it depends on the timer mode. So I have a table for non-PWM mode, I have a table for fast PWM mode, and I have a table for phase correct PWM mode. And if we look at this table, we see if those bits are 0, then OC2A disconnected means I'm not actually going to be toggling the voltage on that output pin, which isn't what I want if I want to generate a true PWM signal. So these last 2 options here are doing what I was describing earlier, clear on up counting or set on up counting and clear on down counting. So that's going to determine, remember, you might have to rewind the video a few minutes when we drew the timer graph and showed the 2 options for whether the PWM signal would initially be high and then go low when the timer was counting up, or vice versa. So setting those bits is going to determine the operation for that pin. And again, we have 2 pins. So if we go back over here, I have OC2B on pin 3. So we have the table I was just looking at was actually for OC2A. So output compare A, but I'm going to have similar tables for compare output mode, phase correct PWM mode for B. So this is the table I want. Or again, I have clear OC2B on up counting, set on down counting, or set on up counting and clear on down counting. So in my case, since I only have something connected to pin 3, which is output compare B, if I look at this register, that means I'm not going to need these 2 COM2 to A1 and COM2 A0 pins. I'm going to need the COM2 B1 and COM2 B0 bits. So again, that was an overwhelming amount of information. Let's kind of recap and write everything all on one screen so we can see it without scrolling back and forth in the datasheet. Okay, so writing the TCCR2A and TCCR2B registers next to each other here so we don't have to scroll back and forth through the datasheet, and labeling all the bits. Our goal is going to be to figure out which bits we need to assign to 1 to set the timer to the mode and set up all the functionality we want. And we're going to do that when we finally get to writing the code in a little bit. So we're kind of going to do process of elimination here. Some of these bits are just blank and have no functionality, so they are just going to be zeros. Some of these bits I mentioned we don't need to worry about for this particular application, so we don't need these force output compare bits. And we are going to be using output compare B, not output compare A, so we do not need to worry about these two bits. They are going to be set to 0. If we were using the output compare A pin for timer 2, then we would need to use these bits instead. Okay, so that leaves us with these bits that we all need to set based on the information we looked up in those tables. So remember whoops, doesn't like when I write at the top, so let's do that somewhere else. The WGM or waveform generation mode bits to set to phase correct PWM mode, I want those set to 001. Remember that came from the table we looked up in the datasheet. It's just a little weird because those bits are split across the two registers. So going from left to right here, I'm going to fill out the most significant bit first. That's WGM22 down here, so that is 0. And then fill the rest in here, 0, 1. So that was for phase correct PWM mode. And then for my clock select bits, I need to set that, I need to turn it on. If I leave those all as 0, my timer is not going to be on. So I want my clock select bits to be equal to 0, 0, 1. That's for with a prescaler of 1. So just kind of normal operating mode, but the timer ticks up once every clock tick. That's going to be 0, 0, 1. And then for my COM bits, I want to choose whether I am setting the pin high on up counting or setting the pin low on up counting. I am going to choose setting low on up counting. So to do that, again, this came from a table in the datasheet. I need to set this to 1, 0. I'm going to pause real quick and go back to double check the datasheet to make sure I did that right. Okay, we are all set here, so now we are going to switch over and finally start writing some code. So I am going to switch to a mostly blank Arduino program where I have, rather than the Arduino setup and loop functions, because setup actually initializes some timer registers in the background without showing you what it's doing. So we have more of a bare metal or blank program here where we have a main function. We're going to have some code that only runs once. And then we have a while one loop, which is code that's going to loop forever, sort of like the Arduino loop function. But again, if you're used to the Arduino setup and loop functions, they're setting up some other things in the background to make other Arduino libraries and functions work as expected. We kind of want to start with a blank slate. So in our main function, we just want to set up those timer control registers. We're going to have TCCR2A and TCCR2B. And we are going to assign to them the values I just wrote out a minute ago in this video. So we're going to do a leading 0B to indicate that this is a binary value. And for TCCR2A, I'm going to do 0, 0, 1, 0, 0, 0, 0, 1. And again, if you want to see where those values came from, you're going to need to go back and rewatch the last few minutes of the video because I don't want to keep toggling back and forth on the screen here. Same thing for TCCR2B. That is pretty much going to be 7 zeros and then a 1. And then adding some comments about what we're actually doing here. Starting on datasheet page 203, we're going to do a few things. Set timer to phase correct PWM mode with the WGM bits. Set prescaler to 1 with the CS bits. And set to clear on up counting, that's with the COM bits. So again, you need to go look up the specific tables in the datasheet for each one of those sets of bits to get the values, map them to the right bits in the register, and then that is how we get these two lines of code that are setting up our timer to do everything we want. But we are not actually modulating the value of the PWM signal yet. To do that, we need to write a value to another register, the OCR2B register. So output compare to B is going to be our register where we store that value between 0 and 255. So Again, that is going to be the equivalent of kind of the value sent to the analogWrite command to give you a duty cycle corresponding to 0 or between 0 and 100%. So if I just write that to some constant value, for example, 127 or 128, that's just going to give me a constant duty cycle of about 50%, and my LED would just be at a partial brightness if I uploaded this program. But that's kind of boring. We want to do the fading behavior, so rather than setting that to a constant value, we are going to make it increase and decrease in a loop. Before I do that, there is something important I'm forgetting. For all of this to work, I do need to set the pin I'm using as an output. So using my data direction register, which if you haven't seen yet, I have other videos covering the data direction and port registers, which are sort of the equivalent of the Arduino pin mode and digital write commands. We are going to set pin 3 as an output, or else none of this is going to work. And then we're going to set up our timer. And then in our code that loops forever, we are just going to ramp up and ramp down duty cycles. So I'm just going to do that using a while loop. So while OCR2B, which is going to start out at 0, is less than 255. You could do this with a for loop if you wanted to. Either way would work. I'm going to increment OCR2B, so OCR2B ++. I can also print out that value of OCR2B if I want to see it in the serial monitor, and then maybe add a short delay here, so delay MS, say 10 milliseconds or something to slow down the fading so it's a little easier for us to see. I'm then going to copy and paste that loop, but change it to, well, OCR2B is greater than 0. I am going to decrement or decrease the OCR2B value. So this is going to do what we saw at the beginning of the video, where OCR2B ramps up and ramps back down, but this time I am going to upload the code and open the serial monitor. So I did that and then realized nothing was printing on the serial monitor because I forgot to initialize serial communication. So always remember that you need this line in your main function if you then plan to use serial print later. And we can see that that OCR2B value is counting up and down, not between 0 and 100. It's going between 0 and 255 because it is an 8-bit register. But if I throw up what I had on the screen earlier again, that is going to make the duty cycle count up to 100% and back down. So I have now successfully faded my LED on and off the hard way. Now, as for the logic of what is actually controlling the duty cycle here, this is just a demonstration. You can make the OC2RB value controlled by whatever you want, and you can find tons of Arduino tutorials out there, including mine and others on the internet, about, for example, making a value depend on a sensor. We have buttons, potentiometers, ultrasonic distance sensors are very popular with Arduino. So if you would like to do something like make the LED brightness react to a sensor, where you dial a knob to treat it like a dimmer switch, or press 2 buttons to increase or decrease the brightness, or react to how close your hand is to an ultrasonic sensor, you could do that by using an equation to assign OCR2B equal to some value based on your sensor reading. I am not going to demonstrate how to do that in this video because there are so many other videos covering inputs and sensors out there. What we are going to talk about a little bit more in this video, though, is controlling this prescaler value and adjusting the frequency of your PWM signals. So far, if I just kind of lazily go back to my PowerPoint here, we've talked about how we adjust the duty cycle by moving this output compare value up and down. But I haven't talked about, well, what if I actually want to change the frequency? And I guess I am going to go to a new slide here. So I mentioned that we have something called a prescaler that can slow the timer down. So for example, instead of stepping up once every clock tick, if I set the prescaler to 8, the timer is only going to increment once every 8 clock ticks. And that's going to make my PWM mode count up and down much slower. So instead of counting up and back down to this, where this period is whatever I calculated earlier, so rather than 256 to count all the way up to the top and then overflow, it's got a period of 512 clock ticks here. So if I do this real time, convert that 512 clock ticks times 62.5 nanoseconds, that gives me 32,000 nanoseconds or 32 microseconds for it to go up and back down. So my corresponding square wave is going to have a period, regardless of what my output compare value is and what the duty cycle is. So remember, the duty cycle is going to be 0 to 100%, what percentage of one period that the square wave is high, but the frequency of the square wave, or the period of the square wave, is fixed. It's going to be this 32 microsecond period from here to here as well. So what if, for some reason, I want to change that? Well, one option I have for doing that is using this prescaler, which if I throw it in a different color here, this is not quite going to be to scale, but say if I set the prescaler to 8, it's going to count up and back down much more slowly. So I have now increased my period by a factor of 8. So 32 microseconds times 8 now gives me a period of 256 microseconds. But that is a pretty coarse adjustment, going all the way from 32 microseconds to 256 microseconds. So we're also going to talk about how we can get a finer adjustment. But first, I want to visualize the effects of changing the prescaler and what that can do to your physical system. So again, I'm getting a little lazy about the editing here because this is becoming a long video, but I'm going to exit out of there, go back to my Arduino code, and ask what happens if I change this prescaler from the minimum value of 1 up to the maximum value. If I go back to this table, the biggest value I can get on the prescaler is 1024 by setting all of my clock select bits to 1. So if I go in here and change those 3 bits to 1 and re-upload my code, let's go take a look at what's actually going on with the LED now. Now, I don't know how well the camera is going to pick this up. We might get some weird artifacts based on the frame rate, but I've tried to increase the speed a little bit or decrease the exposure so to get less blurring, and hopefully this is visible. The LED is still fading on and off, but I am now getting visible flicker on the LED. So I just powered my oscilloscope back on, and I didn't change the scaling at all. So the time axis scale is still the same. And you remember before we could see multiple periods of this square wave, but now I need to zoom way out to be able to see multiple periods on this graph. So the duty cycle is still oscillating between 0 and 100%, but the period between each oscillation is now bigger, and it has gotten big enough that, again, it's not showing up great on the camera. It's going to look a little weird due to the frame rate, but now my human eye can actually detect some flickers. So it is staying on too long. If the goal is to kind of give an illusion of just a continuous brightness at a certain level, it is now slowed down too much due to this larger prescaler value, such that the LED appears that it is flickering to me. So in this case, the prescaler value is too large, and I would want to dial it back down. Now, this is where you might need to play with the prescaler value depending on the physical system you are driving. For example, this could be different for a motor. So for the LED, again, when the prescaler gets too big, we can see it flickering. For the motor, if the prescaler gets too big, you might actually start to see some oscillation in the velocity instead of a constant velocity. But for a motor, if the prescaler is too small, and if the driving frequency is too high, then you might also not get a response out of a motor, because the motor effectively acts like a low-pass filter. So if this frequency is oscillating too quickly, turning on and off, then the motor never really gets to build up any speed. Motor dynamics and time constants and all of that are kind of a totally separate topic for a whole series of videos that we could go into. I do have an intro circuit theory playlist that you could check out if you want to learn about time constants. But point being, there isn't a single correct value for that prescaler. It's going to depend on the physical system you're driving, whether it's an LED, a motor, or something else that you are using a PWM signal to control. It's not necessarily just always going to be this clear-cut linear relationship where 0% duty cycle corresponds to off, 100% duty cycle corresponds to completely on, and you get a linear relationship in between. Even with the LED, you may have noticed back earlier in the video that it didn't necessarily look like a linear brightness fade as the duty cycle went between 0 and 100%. You might get the same thing with a motor where it's not necessarily a linear relationship between speed and duty cycle because you have things like internal friction in the motor where it might not be able to overcome at very low duty cycles, so it might not spin at all. Again, there's a whole lot going on there, but point being, you now have the tools to control the duty cycle and to very coarsely control the period by the factors of this prescaler, so 1, 8, and so on. Next, we are going to look at how you can even more precisely control the period if, for example, you wanted to do something like control a servo, which I don't have handy on my desk to grab at the moment, but we'll switch back to the computer and talk about how the servo control protocol requires a square wave at a specific frequency, so how you can use the timers to generate that. Now, introducing servo motors on their own is really a topic for another video. In this video, we're specifically going to talk about the servo control protocol, or PWM signal, used to control servo motors, which is different from the PWM signal you would use to control the speed of a DC motor. So that signal is going to have a duty cycle that oscillates between 0 and 100%. That is not what we are doing. Wow, it really doesn't like when I write up there. For servos. Servos are going to have a frequency or a pulse train or square wave signal with a period of 20 milliseconds. In other words, this is a 50 hertz square wave, and the positive pulse width is going to vary between 1 and 2 milliseconds. So this is not varying between 0 and 100% duty cycle. We're going to between about 5 and 10% duty cycle. And for a little servo motor, my artist's rendering here of a top view of the servo with a little plastic servo horn, that is going to correspond to a range of about 0 to 180 degrees for a positional control servo. Again, actually seeing those servos and everything is a separate video. You can find tons of tutorials about them. We are asking, okay, how do we generate this PWM signal if the frequency of our square wave is kind of fixed by the amount of time it takes the counter to count up and back down, and I only have these fixed prescaler values, so 1, 8, and so on, so I can't really easily fine-tune this frequency or period to get an exact 20 millisecond period. And the way we're going to use that is to use another PWM mode available in the datasheet that is sort of similar to the clear timer on compare mode that we saw before, where instead of counting up to a default max value of 255, we are now going to be able to select the value that the timer will count up to, where instead of resetting, it will now then count back down when it reaches that value. So by choosing this new top value here, instead of this default top value of 255 for an 8-bit register, we can then fine-tune this period to get exactly what we want, in this case, a period of 20 milliseconds for the servo control protocol. We will then select another output compare value, just like we did before, that is going to be used to generate the corresponding PWM signals. So, to do that, we are first going to hop over to the datasheet and take a look at what timer mode we are going to need. So I'm going to exit there, pull up my datasheet, scroll down a bit. I was up a little far. We're going to skip ahead a few pages. So here we have our waveform generation mode table again. And we notice that there is another phase-correct PWM mode 5 here in this table, where my WGM bits are going to be 1, 0, 1 instead of 0, 0, 1. But the difference is this top column. So previously, for mode 1, the top value was always going to be 255, or 0xFF in hex. Here, the top value is going to be set by the corresponding OCR A register. So again, if I switch back to my drawing here, that register is what is going to allow us to select this value, which is then going to correspond to the period here according to this equation. So the period there in nanoseconds is going to be equal to 62.5, which is actually, I didn't give myself enough space to write that out. I'm going to do it down here. Period of my PWM signal in nanoseconds is going to be equal to 62.5 nanoseconds, which is still the period of 1 clock tick. 1 clock tick times 2, because the timer is counting up and back down, times my top value times my prescaler value. So technically there, if you have a desired period, you have one equation with two unknowns. You can select anything between 0 and 255 for the top value, and then the prescaler has those values of 1, 8, and so on. But since there are only limited values available for the prescaler, you can sort of do a guess and check and pick a value for the prescaler, then calculate the top values. So I am just going to take a shortcut here and to tell you that for the servo control period that we want, we are going to pick a prescaler of 1024. So if I choose a prescaler of 1024 and then solve this equation for top, because I know a desired period of 20 milliseconds, being careful about my units because this is nanoseconds over here. I'm not going to write out all of the math, but it turns out that I get a top value of about 156. So rather than counting up all the way to 255, I'm going to count up to 156, and with a prescaler of 1024, that gives me the period that I need for servo control, where I can now, again, adjust my output compare value to control the angle of the servo. Now, again, if you're familiar with Arduino and you've used the servo library before, there is a Arduino library that will just do this very neatly for you and let you write an angle to the servo where you don't have to actually worry about the PWM signal at all, and you just send it an angle between 0 and 180 degrees. But again, as with most Arduino libraries and functions, this is kind of totally masking what is actually going on behind the scenes, where it is also using timers to generate these PWM signals. So let's switch back over to the code and write code that is going to allow us to manually control a servo with an 8-bit timer. So to do this, we are just going to modify our existing code. We are still going to have pin 3 as an output, and we are going to keep most of what's in our timer control registers. We're going to set the prescaler to 1024. I didn't change that comment earlier. We're going to leave it to clear on upcounting, so we're not going to change the COM bits. What we need to change is those WGM bits. So if I go to my datasheet here, again, I now want mode 5, where the WGM bits are going to be 1, 0, 1. And remember, this WGM22 bit is here in TCC R2B. So I'm going to switch back over to my code, and I need to change that third bit in my code to 1. So here I have my PWM demonstration. I'm going to change this bit to 1. So I have set it to phase correct PWM mode, but now my top value is going to be the corresponding OCR-A. In this case, that's going to be OCR2A for timer 2. So a little bit of a weird thing on the datasheet where they don't have the 2 in there. But I'm going to set my OCR2A register. So set top value for timer. OCR2A is going to be that value I calculated earlier, which is 156. And now I can also still have code that is going to increase and decrease OCR2B, which is going to be my output compare value. But remember that for a servo control PWM signal, I'm not going between 0 and 100% duty cycle. I'm going between 5 and 10%. So if I, on the fly here, kind of calculate about 5% of that 156, that is, I'm going to round down to an initial value of 7, and then 10% of 156, let's say we're going to call that 16, so I'm going to kind of round up and down to the extremes of that range. So I am initially going to set OCR2B to 7, and then while it is less than 16, I'm going to increase it by 1. I'm going to add a little longer, much longer delay in here, so this is more visible when I go operate the servo later. And then while it is less than 7, I'm going to decrease it, again, with a longer delay. So you might notice already that with only an 8-bit timer, we are not going to get very good angular resolution with the servo. I'm not going to be able to control it in 1 degree increments because these registers are storing integer values. They're not floats. I cannot set this to 7.5 or 7.9 to get finer angular resolution, so I really only have a handful of values here that I'm going to be able to set the servo to. So I'm demonstrating all of this with an 8-bit timer. The ATmega 328P also has a 16-bit timer, but there's only one of those. So if you are using your 16-bit timer for something else, then maybe you would be okay. If I only need to move my servo in 45 or 90 degree increments, maybe this is good enough for you. So if I go connect and upload the code to my Arduino, again, I'm getting lazy with editing, so I'm just going to wheel away as I go plug that in. And upload this and look at serial monitor. I should see this OCR2B value now just changing much more coarsely with a longer delay. So I'm going to open my serial monitor, and I now see my OCR2B value counting up from 7 to 16 and then back down just as expected. So in a minute, we are going to switch over to filming the Arduino again and look at what this looks like once a physical servo is plugged in. Before I do that, I want to briefly talk about, okay, well, why would we want to do any of this? That looked like an awful lot of work. Why wouldn't you just use the Arduino Servo library? And if you pull up the documentation page for the Arduino Servo library, it does talk about how it lets you control up to 12 motors, and it does all of this using a single timer, which is pretty convenient, a lot easier than writing. We just went through everything to control one servo, let alone controlling 12 of them. But note that the top-level Arduino documentation, which is really kind of intended for people who don't have a lot of coding experience, making this easy to get into, doesn't really explain what's going on behind the scenes. It has this little vague note here how use of the library disables analogWrite on pins 9 and 10, whether or not there is a servo on those pins, but it doesn't really tell you why. But if you actually understand how timers work and know that the Arduino UNO R3 only has 3 timers to go around, if you go take a look at the pinout diagram and look at pins 9 and 10, you'll see, okay, those are marked as PWM pins, but they have this OC1A and OC1B on them. So these pins are tied to timer 1. This is the 16-bit timer, which we haven't been using. So basically, use of the servo library is hogging timer 1 and preventing analogWrite from working on these pins. So if you understand that, then at least you know what's going on behind the scenes and why analogWrite doesn't work there anymore, whereas if you don't really know anything about timers, then that might just be kind of a mystery. This can also become a problem, for example, when mixing third-party Arduino libraries or other Arduino functions that depend on timing, like the millis function, that might assume they have exclusive access to a timer. Think of it like a group of people that only have 3 stopwatches to go around. If one person is hogging the stopwatch or somebody else tries to grab the stopwatch while you were in the middle of using it, you can run into weird conflicts in your code depending on which parts of your code or which libraries assume they have access to a timer. So if you do it all manually yourself like this, even though it's painful, then at least you know exactly what is going on in your code. So with that, we are done with the code. Again, we are going to switch over to the Arduino and see what this looks like on the physical servo. All right, now looking at what we have here, we have the servo hooked up to the Arduino. It just has 3 wires, power, ground, and signal. And we again have the oscilloscope hooked up, looking at the output of the PWM signal or the control signal for the servo, where we have a duty cycle changing, now not between 0 and 100%, but between about 5 and 10%. So oscillating between about a 1 and 2 millisecond pulse width. And again, since I'm only using an 8-bit timer and I have such a low resolution, then we can see these pretty discrete jumps in the duty cycle as this pulse jumps from one position to the next with a 1-second delay in between. And we can see the corresponding discrete changes in the angular position of the servo, where since I am only using an 8-bit timer, I cannot really do better than that. And that could be fine, again, for a mechanism where I only need the servo to oscillate between, say, 0 and 90 degrees. But if I need finer or more accurate position control, then I would need to do that with the 16-bit timer myself, doing it manually with the registers as we saw. Same process, but you would need to go look up the different registers for timer 1 in the datasheet, or you could use the Arduino Servo library. Okay, hopefully after this nearly hour-long video, you now have a better understanding of how to manually generate a PWM signal instead of using the Arduino analogWrite function or the Servo library for applications like controlling the brightness of an LED, controlling the speed of a DC motor, which is going to require some additional hardware like a transistor or an H-bridge that I did not go over in this video, but I do have other videos about that on my channel, or for controlling a servo motor, again, instead of using the Arduino Servo library. Thanks for watching.